Welcome to section 4, performance metrics for fraud detection. This is lecture 14, understanding the cost of misclassification. So I've implemented the same XGBoost model that we used in the last section and in lecture 13 for the purposes of producing the confusion matrix, just to see, the overall classification performance of the model. We are reasonably satisfied with that. Then what I wanted to show is that the confusion matrix, or the output of that itself, can be inspected as a Python object itself, so as a data object, and we can actually slice it and access the elements within this matrix that it returns, right? So this array of data, we can actually inspect it and then use that in a programmatic fashion to calculate what this actually costs from an operational perspective. So, we're training this model in isolation. It's on our desktops, it's in a notebook. This could be done in the cloud, but we're obviously not doing this for fun. We're doing it to build something that can detect models for ourselves, for our business, for our organizations. And, we're using real world data to do this. And there's real world consequences for these misclassifications. And that's what we'd like to try and do, is to understand that and attach a cost to each of those so that we can come up with a holistic cost, or a total cost of fraud for each of the models that we train. All right. So I can, like I said, access each of these elements within the array. And what I've done here is I've assigned a fictitious cost to each of the classification quadrants in the confusion matrix. So, for example, the cost of true positives, that's the cost of correctly identifying a customer as fraudulent, if they are fraudulent. And we can say, for example, that costs $1 because it's just the cost of running running inference, running the actual machine learning model itself. And we can attach or attribute a classification cost from an operational perspective. It's low, but it's obviously saving us. Maybe there's some opportunity cost that we're missing, but we'll see that with the costs of the other misclassifications. Then the same for the true negatives. So these are the good customers that we correctly identify as good customers. I guess, if we're catching a lot of those, the model's doing what it's supposed to do. There's no cost besides the cost of running the actual algorithm or the train model, like I mentioned. So we've also given that a cost of 1. Then for the false positives, there is a more significant cost, and I've given it a cost of 10. But remember, this is just arbitrary costs. Each would, make more sense within your own organization. And these costs you would have to actually go and, work out by engaging with stakeholders, really understanding your systems, your processes, and how everything ties together. So that's not something that you would probably do in isolation as a data scientist. I think you'd have to lean on other people within your fraudulent department and other stakeholders who have a good, understanding of operationally how these things would work. But the cost here is, if it's $10 and we've only got 3 of them, that's adds up to $30 potentially. But here we experiencing like a bad customer experience. We are telling customers that they are bad when they're not. So we effectively applying some sort of friction. We're locking their accounts. We're blocking them from transactions, etc. Fraud analysts and investigators might have to unlock their process, or rather their account. That takes time. We can attribute a cost to that. We can say it's a portion of the time spent for that analyst to unlock their profile, to investigate them, to pick up the phone and to verify them. And based on the salary of that fraud analyst, we can attribute a cost that way. And then lastly, the cost of false negatives. So these are the cases where it is a fraudulent customer, but we haven't detected them, right? And there's 6 of them in this case. And these can also be quite severe, usually the most severe, and I've given it a cost of $100. And that you can, determine by your average cost of fraud historically within your organization. You would have some sort of a track record of fraudulent cases, and you would use that to build up your training set and your test set, and that's what informs your actual target variables, that historical record of fraud. And then you can always attribute that average cost per fraudulent case here, because these ones that you miss, they are going to go through, they're going to pass through your processes, they're going to transact, they're going to, do some kind of fraudulent activity. You're going to get a chargeback report from the bank, and there will be some cost for you as an organization. There's reputational risk. You would, your reputation with your kind of third party financial services providers, and these people would influence it. So, they would be, that relationship would be negatively impacted. So you can also factor that into it. Right. And then we can work out the total cost of fraud overall for the model. So we can take each of these classifications from the quadrants that we've sliced, and have access to. We can take each of those, which is just the number of misclassifications within that quadrant, and we can apply a costing, the hard-coded costing. So for the number of true negatives, I can slice it and find them. There's 28,000 of them, and then I can apply the cost per true negative. And then I can do the same for each of the different misclassifications, and then come up with the total cost of fraud for that model specifically. So, we can say this model is going to cost us $29,000, for example, this exercise to detect fraud. Right? Then we can do the same with the logistic regression model. So I've just trained the baseline logistic regression model again, the exact same data, and then I've generated the same model that came out much earlier in the lectures, and performed the same process again. I've used the confusion matrix for that model specifically, taken all the elements, added up their cost per unit or cost per misclassification, and then come up with a total cost of fraud that's slightly higher than the XGBoost cost. So we can say here, from an operational perspective, we'd likely prefer and gravitate towards the XGBoost model, because it's going to cost us slightly less than the logistic regression model.